The second lab in Physics 2211 was to observe an object falling somewhat slowly and compare these observations to two different computational models, one that only accounted for the forces of gravity and one that accounted for both the force of gravity and the force of drag. In order to create these computational models, we first must understand the concepts that the models are predicting. For this, we will take a closer look at Newton's second law, which states that the change in momentum for an object is equal to the net force on the object. First, we will solve for the net force, since that is what we are trying to model in our computational models. To do this, we shift delta p and Fnet. Then we change delta p to equal mass times the final velocity minus the initial velocity, and we will use this equation to find the net force, which will equal the sum of all forces on the object. To find the average velocity using the known positions of an object, we integrate the fundamental principle twice with respect to time. In one of our computational models, we predict the force of drag by multiplying the speed squared by a drag coefficient determined by looking at the observed model. In order to find the speed, however, we find the magnitude of the velocity. Using all this, we can predict the drag force by saying that the net force on the object in the y direction is equal to the force of gravity plus the force of drag. In this lab, my observed object with a red Solo cup turned so the open side faced the ground. I positioned the origin so the cup started at the origin and fell in the negative y direction. Using Tracker, I found the cup's position at each time interval, which in this case was 1/30th of a second, the video frame rate. I then used this data to plot a position versus time graph in Google Sheets. I used GlowScript to create a computational model that could predict the motion of the falling red Solo cup. Here in the code I used for my first model, which only counted for the force of gravity. Some key elements to note in my code is the mass of the object, which for the cup was 9.07 grams, or, in this case, 0.00907 kilograms. I made delta E(t) equal to the frame rate of my video, which was 1/30th of a second. The magnitude of gravity that I used was 9.8 meters per second squared. The force of gravity, which in this model was also equal to the net force on the object, was the negative product of the mass of the cup times gravity. And finally, in order to update the velocity of the cup in each iteration, I divided the net force by the mass, multiplied that by delta t, and then finally added that to the previous velocity found in the loop. In order to create the computational model that accounted for both the force of gravity and the force of drag, I used a similar process, but changed the net force to equal the sum of the force of gravity and the force of drag. The mass and gravity did not change, and I found my drag coefficient to be 0.01572, which made it so that the model lined up with the last point in the observed position. I calculated the force of drag by multiplying this coefficient by the square of speed, which in this case is the magnitude of velocity. Using this new net force, I updated the new velocity using the same formula as I used before. I then plotted all the positions versus time on the same graph in order to compare the results. In this graph, the blue line is the observed position from the tracker analysis, the red line is the computational model that only accounted for the force of gravity, and the yellow line is the computational model that accounts for both the force of gravity and the force of drag. All three models started close together, but the model that only accounted for the force of gravity quickly deviated, and predicted that the cup fell further than it actually did in the same amount of time. This makes sense, since this model did not have any force acting against the force of gravity to slow the cup down, and as such, it was constantly accelerating. The observed model and the model that accounted for both the force of drag and the force of gravity deviated slightly in the middle of this time section, but then came back together near the end. The slight deviation is probably due to the tracker system of analysis, as selecting the center of mass of the cup became harder to accurately do as the cup accelerated since the frames got more and more blurry. The observed model and the computational model that accounted for both the force of gravity and the force of drag predicted a terminal velocity. This makes sense, as the drag force would eventually equal the force of gravity, which makes the net force on the cup equal to 0. This means that these models predict a time where there will be 0 net force, since the falling object will no longer be accelerating. The model that only accounts for gravity does not predict a terminal velocity, since it predicts that the cup will continue to accelerate as time increases. Now, what if we imagine that the initial object was initially thrown downward? Would this terminal velocity change? Well, if the cup was initially thrown downward instead of just dropped from rest, it would still have the same terminal velocity. It would just reach it quicker. This can be seen from the two graphs from GlowScript. The graph on the left shows the velocity versus time of the cup dropped from rest, accounting for both the force of gravity and the force of drag. As you can see, the y-intercept is 0, and the graph eventually goes to an asymptote of a little more than 8/3 meters per second. The graph on the right is in the same function, but with a starting velocity equal to negative 2.1 meters per second. This graph also goes to the same asymptote, but the slope evens out a little before the slope of the graph on the left. This makes sense as the initial velocity does not affect the force of gravity, and as such, the drag force will eventually equal that, which would create a zero net force, leading to a constant velocity. And that is all I have for the second lab in Physics 2211. Thanks for watching.